Here's the beginning of the series of logic lectures that are created for two different classes, and the textbook for the whole courses and for our series is Logic for Computer Science, Classical and Non-Classical, published by Springer, and I am the author. I'm Anita Wasilewska, and I am the author. Okay, so we start with chapter 1, that's how it should be, and it is really an introduction which motivates the development of logic and logics for computer science. So, and here's our plan. I have 5 parts. They're short parts, but I split them into the parts. So, first 2 are about logic for mathematics. It means when and how and when and why logic became important to mathematics and for building the foundations of mathematics. And we'll cover historical logical paradoxes and semantical paradoxes. And the second part, which is slide set 2, are logic for computer science, and which are important, we'll talk about the importance of certain non-classical logic in application, as the application to computer science, and also some of them were and are being developed by computer science, and these are all classical, of course, our classical logic, but also intuitionistic, modal, temporal, man-evaluate logic. So, and then we'll talk a little bit about reasoning in artificial intelligence. And again, examples I give are historical. So today is all historical beginnings of the whole fields. So logics for mathematics, and we talk about logical paradoxes. Okay, until the end of 19th century, mathematical theories used to be built in an intuitive and not formal way. For centuries, mathematics was built like that. But historical development of mathematics has shown that it's not sufficient to build mathematical theories only on intuitive understanding of the notions, and that are the 2 or 3 examples which move the whole development of thinking about reasoning in mathematics, which is logic and building foundation of mathematics forward, and it became a field of mathematics itself. So, first, that was what Russell said. By a set, we mean intuitively a collection of objects. For example, the set of all integers or the set of all students in a class. The objects that make up a set are called members. Now we call them elements, but they use member of a set. And of course, sets might be themselves members of other sets. For example, the set of all subset of integers has sets at its members. Most sets are not members of themselves. So, for example, the set of all students is not a member of itself, because the set of all students is not a student. However, there might be sets that belong to themselves. For example, set of all sets is a set. And here comes the Russell paradox. That reasoning I carefully read and showed that was Russell reasoning. Russell paradox, 1902, consider the set A of all those set X such that X is not member of X, because we know that some sets are not members of itself. Clearly, if you A is A, the set A are the set of all sets X such that X is not member of X. Of course, A is a member of A, if and only if A is not member of A. So, if A is a member of A, the A is not also a member of A. And vice versa, if A is not member of A, then A is a member of A. In any case, A is a member of A, and A is not member of A. Contradiction. There's something wrong with our notion of set. And that really moved development of thinking. What is a set? It means thinking about mathematics into much more precise direction. And of course, now I'm going to show you example. Of course, before I explain you the theory of types and so on, we already know, because the way you learn, and we learn about the sets, we write, for example, X is a members element of X, and here you use small letter for elements and capital letter for a set. So in this way, you know that you cannot have that X is a member of X, because if you have it, you have Russell paradox. So the way you learn about sets, you already learn the proper thinking about the sets. Of course, you can say that this is a set. It can be a member of another set which has, for example, this is a set A or X, and it has 1, 2, 3 elements. And this means we write that 1 is element of the set, which has 1 as an only element, and this set has 3 elements. You have that this is element of this set, let's call it, and also you have this is element of our set, and also you have another element, because I just put it as element of a set. These are elements, and this is element of the set, which is set itself, and so on. But also you can write, for example, that this is also element of a set. This set is element of a set. This is set which has this element as an only element. So we, for the finite set, that's how we write, and to distinguish elements and sets can be elements of another set, and so on. So, and that all came from the way to treat and to distinguish elements and the sets can be elements of other sets and so on, came from Russell and what he called the theory of types. So the idea is that every object must have a definite non-negative integer that as its type assigned to it. So when you say X is a member of a set Y, is meaningful only if the type of Y is greater than the type of X. So you see type, and here is greater type. So that's why this greater type we adopted writing by capital letter instead of writing X elements of X or X element of Y. Again, following the Russell distinction, of course you can write it like that, but you have to know that type of Y is greater than type of X. And in set theory books, mathematicians love to write it like that instead of using our common notation, because they know that if you write like that and it's correct expression, it means the type of this is higher than that. So you know if you write that. But to be safe, we adopted the notation using capital letters for set and small elements for X. So Russell theory of types guarantees that it is meaningless to say set belongs to itself. And the solution is the set A as stated as Russell paradox does not exist. And that was developed in 1913 by Whitehead and Russell and so on. Of course, in particular, the set of all sets does not exist, because set of all sets has the property that it belongs to itself. So, so that's how it started, and that's how we now teach, and that's how you learn your basic sets with such notations and so on. So logical paradoxes are also called logical antinomies. Paradoxes, antinomies. They are called logical, and so logical paradoxes are paradoxes concerning the notion of a set. They're not set paradoxes, they are logical paradoxes. And development of axiomatic set theory is the most important field in modern mathematics. Okay, because the axiomatic set theory was developed and became one of the most important fields of modern mathematics, and specifically of mathematical logic and foundation of mathematics. So the whole fields, axiomatic set theory is a part of foundations, of building foundations of mathematics, and this is built on mathematical logic, and so we'll talk about it later. And all those fields resulted from the search for solution of various logical paradoxes. And first paradoxes-free axiomatic set theory developed by Zermelo in 1908. So 1902 was Russell, and then the whole development of the notion of the set in the form of axiomatic set theory it still exists, but what was the very, very intense works. And the first paradoxes-free axiomatic set theory was developed by Zermelo in 1908. So, so we did the Russell paradox. Other logical paradoxes are called Cantor and Burali-Forti. and they were stated at the end of 19th century. Cantor paradox involved the theory of cardinal numbers, and Buratti-Forti paradox, ordinal numbers. Okay, cardinal numbers, what is a cardinal number? So we say that two sets have the same cardinality, this nice cardinality equal y, if and only if there is one-one correspondence that maps x and y. So you will say that, what does it mean? Normally you say that they have the same number of elements, right? You have a set which have some elements, can be infinite. You have another set. Let's put flowers. 1, 2, 3, 4, 5. And we treat each flower, and you count the flowers. 1 goes to here, 3 goes here, 4 goes here, 5 goes here, and I need still 6. So you have 1-1 correspondence between our set of numbers and our set of flowers, and that's how you count. So you say that cardinality of x, y equals cardinality of y. It means in finite set is number of elements of x is equals number of elements of y, because you use the word number for the finite set because you have sort of a number. But with infinite sets, you can have infinite sets which have the same cardinality. For example, you can have infinite set n of natural numbers, just to remind you, 0, 1, 2, and let's say a function which to each number assign n to n, so it would map the set of natural numbers 1, 1 onto set of even numbers. 0 is even. 2, 4, 6. 0, 1, 2. And you have 1, 1 mapping. So you can say both sets are infinite. So you say that cardinality of n equal cardinality of odd, even numbers, if you call that even. Right? So for infinite sets, you use the notion of cardinality. And and we say that the cardinality of one set is less equal cardinality if x is equinumerous. It means there is 1, 1 correspondence which maps x into the subset. Of course, you can say that if you can say that that function also you can say less equal because of cardinality, even because even are a subset of n, but is equal because I showed the mapping. This mapping shows that it's equal, and this is subset, so you can say less equal, and that mapping shows that it's really equal. And also, we say the cardinality of one set is less that cardinality, if it's less equal, it's like, and they are not. So in the sense that is, you know, if you have for finite sets, which is numbers, n is less equal m, you say n is less m, means that n is less equal m, and n is not equal m. So the same holds for any cardinal numbers. And Cantor proved, Cantor theorem, that for any set, cardinality of x is cardinality of px. Px, now the other important set is if you have a set x, px is set of all subsets of x. Another notation for px, capital X, is 2 to the power x, capital X. So this is the set of all subset of x, and Cantor show that if you take a set and you take the set of all subsets, you get more elements. You see, you get more elements. Of course, that we know for the finite sets, when you look at this, if you have A is finite, and you have the set of all subset of A, cardinality, let's say cardinality A equal n, so the cardinality of the set of all subset of A is 2 to the power n. So that's why also for finite sets, so if you have a set of n elements, the set of all subset has 2 to the power n. You prove it by mathematical induction. And of course, you also prove that n is less than 2 to the power n. So for the finite sets, you prove, this is a proof that cardinality of A is less than cardinality of PA for finite sets. And Cantor proved that it holds for any infinite set. Also, Schroeder-Bernstein proved that those cardinalities, which they called cardinal numbers, behave in a similar way as numbers, right? We know for numbers you have n less equal m and m less equal n. We have that n equal m, right? So our numbers behave like that. Numbers are cardinality of finite sets. Schroeder-Bernstein show that for infinite sets, so you can think that this is like infinity. Infinite, if they have cardinality, is the number assigned to a set which is infinite, and they are different cardinal numbers. So that the cardinal numbers behave in the same way as normal numbers. And Cantor paradox, 1899. Let C be the universal set, that is the set of all sets. Let's now PC be PC, the set of all subset of the set of all set, is a subset of the set of all sets. So cardinality of the set of all subset of C is less equal cardinality C. On the other hand, by Cantor theorem, we know that cardinality C is less than cardinality PC. That is a Cantor theorem. And of course, cardinality of A is less equal cardinality of A, so you have less equal here. So you get the cardinality C is less equal cardinality of the set of all subsets C. By Cantor-Bernstein theorem, we have that cardinality of the set of all subsets C is the same as cardinality of C, contradiction for Cantor theorem. So, solution, universal set does not exist. So we know already we have a lot of sets, but universal set does not exist. Otherwise, it would contradict the Cantor theorem. Now, I'm not going to go into that, but it's just to state, or the Burlati-Forti paradox deals with ordinal numbers. Ordinal numbers are special measures assigned to ordered sets. And Burlati and Forti, again, 1897, said the following. Given any ordinal number, we know that there is still a larger ordinal number. But the ordinal number determined by the set of all ordinal numbers is the larger ordinal numbers. Solution, the set of all ordinal numbers does not exist. So it's not only the set of all subset does not exist, but set of all ordinal numbers does not exist. So another solution to logical paradoxes is to reject the assumption that for every property Px, there is a corresponding set of all objects S that satisfy Px. So remember, we write, you see, set of x Px, property x, property, P stands property. So, and we know, like for example, the set of n in n, that n plus 1 equals 3, this is our property Pn. So that set would be 2. 3 minus 1, n equal 2. So the set of all x for which the property holds, you can find this set. So the problem is that you can do it not for all property and not for all sets. If you think about Russell paradox, that Russell paradox proves that there is no set defined by the property Px. X is the set of all sets that do not belong to themselves. Such set does not exist. So another important consequence or solution to logical paradoxes is that there are properties Px that corresponding sets does not exist. So we have to be also careful when to write such a thing, because sometimes there are properties such that the set of all x that Px do not exist. And this seems like, and that also led to development of pieces of logic. So Cantor paradox shows that there is no set A defined by property Px, there is universal set. Burlati-Forti paradox says that the property Px, there is a set X that contains all ordinal numbers, that there's no set for which that would satisfy, and there's plenty of others. So in general, that statement that we write set of x Px, we have to be very careful, and we show that the property defines a set, because sometimes it might not define set within the paradoxes-free mathematics or set theory in this case. Okay, so the more radical interpretation of those logical paradoxes came from Brouwer and his intuitionist school. I bring it here because we will be studying not only classical logic, but intuitionistic logic. And intuitionistic logic is the first most rival logic to classical logic. So intuitionists refuse to accept the universality of certain basic logical laws, like excluded middle, which says for any statement A, you have A or not A is always true statement. So for intuitionists, the excluded middle law is true for finite sets. If you say property of finite set, you have property or not, but it's invalid to just extend it to all other sets. So in a sense, intuitionist concept of infinite sets differ from the classical one. And the basic difference between classical and intuitionist mathematics, because mathematics is built on sets, is also interpretation of the word exist. In classical mathematics, proof that existence of object X, so you want to prove there is X for which Px holds, you can do it. How you can do it? You can do it, okay, assume not. So it means there is no X Px. Now you have the Morgan law. So that is equivalent for all X not Px. And you work with this and get contradiction. So it means that this is true. So you can prove existence of something by contradiction. And many mathematical theorems, many existence of solution of certain type of differential equations are proved by that beautiful proof by contradiction methods. You say that, oh, if a differential equation is such, such, and such, so solution exists, but we don't know how to find them. So intuitionist universe, we are justified in asserting existence of an object having property if we only prove by effective method of constructing or finding such an object. You cannot pull out objects out of your magical hat by the proof by contradiction reasoning. And proof by contradiction is really based by excluded middle and so on. And the Morgan law, you see here you have the Morgan law existence. This you have the Morgan law. The Morgan law in intuitionist universe, that the Morgan law is invalid. And we will study intuitionistic logic. Now, the other type of paradoxes are called semantic paradoxes. And here, so we mathematicians develop axiomatic theories which to axiomatic set theory to deal with logical paradoxes. But it happens that even consistent set of axioms do not prevent occurrence of another kind of paradox. See, that's how it's beautiful. You solve one problem, and then somebody comes like, yeah, it's nicely, yeah, we got rid of it. But look at such an example. 1906, few years after Russell. And now I'm going to read it carefully. Let A denote the set of all positive integers which can be defined in the English language by means of a sentence containing at most 1,000 letters. Of course, this set is finite because the set of all sentences contain at most 200 letters is a finite. So this set is finite. So if the set is finite, there is a positive integer which do not belong to that set A. And now look at this sentence. I put everything on one side because in colors, right? So we know that there is positive integer from that definition which do not belong to A. And look at this sentence. N is the least positive integer which cannot be defined by the means of a sentence of the English language containing at most 1,000 letters. Nice sentence. N is the least positive integer which cannot be defined by the means of a sentence in English language containing at most 1,000 letters. So fulfilling that. So this sentence has less than 1,000 letters and defines that integer. So that integer belongs to A. But N does not belong by the definition of N because N cannot be defined by the means of the sentence. Contradiction. And that is called semantic paradox. So, what is the solution? So really, the solution is that we did not say in this definition, you see, you mix the English language, you defined integer in terms of the sentences of English language containing 1,000 letters, but integer really belongs to arithmetic. You can define certain integers or certain numbers by only within your arithmetic or of the numbers. So the paradox resulted entirely from the fact that we did not say precisely what notions and sentences belong to arithmetic and what notions concern the arithmetic. And also you have those English language and so on. So, of course, we didn't talk about and examine arithmetic as the fixed closed deductive system, which we will be doing, and also incorrectly mix the natural language and mathematical language. So the solution is that we have to always clearly distinguish between the language of the theory, like arithmetic, and the language in which we talk about the theory, and this is called a meta-language. In general, we must clearly distinguish a formal theory from meta-theory. We will develop the notion what is the language of the theory, what is the formal language, what belongs to the theory, what does not belong to meta-theory. So if you do it in a proper way, such paradoxes cannot appear. And so that is one of the goals of the course, to set these levels of language of theory, meta theory, correctly. And now you have another paradox, very old. So a man says, I am lying. If he is lying, then what he says is true. And so he's not lying. If he is not lying, then what he says is not true. So he is lying. Contradiction. Where is the problem? Of course, those paradoxes arise because the concept of I am true, this sentence is true, I am lying, should not occur in the language of the theory. They belong to the meta language. If you have that division, you sort it out, you will not have that paradox. It means they belong to a language that talks about the theory. A liar paradox is a corrected version of the paradox stated by Epimenides, and which is called the Christian paradox. And Christian philosopher Epimenides said, all Christians are liars if what he says is true, meta-language, then since he's a Christian, it must be false, and what he said is false, thus there is a Christian who is not a liar, contradiction. So now we'll take care of it also. Another type of paradoxes, I call it puzzles. And then they belong to computer science. So they are a little bit, develop a little bit later, but they are very important because, again, they moved foundation of computer science, they move thinking about our human reasoning and so on in a very interesting new directions. So the use of classical logic in computer science now is known. For example, existed Prolog and logic programming as separate fields of computer science is an example of that. Intuitionistic logic in the form of Martin Löw theory of types, beautiful generalization of Russell theory of types from 1982, provides a complete theory of the process of program specification, construction, and verification. And similar has been developed by Constable in 1971, Beeson in 1983. So intuitionistic logic has a very plays very important part of, for example, in theory of programs, and hence in computer science, correctness of programs. Because, as I said before, intuitionistic logic has that constructive part in it. To prove existence, you have to have some constructions. So if you want to, when you want to prove correctness of programs, you need to have some assurance that your proof is not rabbit out of the hat. It has to be a real concrete proof. Now, the other logics which play a very important part in computer science are modal logics. They were created in 1918 by Lewis, and they were created to avoid paradoxes of classical implication. A false sentence implies any sentence, and he proposed a new interpretation of logical implication. And his idea was to distinguish necessary truth from possible truth. And so that was called a modal logic, was created. And we have a whole chapter about modal logic, so we'll go in depth, and also have a chapter about intuitionistic logic and so on, so we'll go in depth into that. Modal logics in computer science are used also as a tool for analyzing such notions of knowledge, belief, tense. And also modal logics has been employed in the form dynamic logic, very important, Harrell, 1979, to facilitate the statement and the proof of properties of programs. And hundreds modal logics are constantly being very important modal logics invented by computer scientists. So temporal logics, another very important type of logic, created for specification and verification of concurrent programs, Harrell and Parikh, 1983, for specification of hardware circuits by Halpern, Mana, and Meshkovsky, 83, temporal logic, and also temporal logic are still being created for different reasons and in different applications. Were also used to specify, clarify the concept of causation and the role of common sense reasoning. So temporal logic, very important type of logic created by computer scientists and being applied by computer scientists. So the development of new logics and application of logics to different areas of computer science, and in particular to artificial intelligence, is a subject of the book or books itself and is beyond our logic course. But it justifies why in our course, in our book, we talk about non-classical logic. So the book examines in detail the classical logic and some aspects of intuitionistic logic, relationship with classical logic. We will introduce the standard many-valued logic. We examine two very important also in computer science, modal logic S4, S5, which are called also knowledge. S5 is called knowledge logic, and has connection with fuzzy sets, rough sets, and very important logic, and also relationship between modal and intuitionistic logic. So now we have computer science puzzles. We had mathematical puzzles, and now we have computer science puzzles. So, reasoning in distributive system. You have problem 7884. Two divisions of an army camp on two hilltops overlooking a common valley. In the valley, there is an enemy. If both divisions attack the enemy simultaneously, they will win the battle. If one division attacks, it will be defeated. So, the divisions do not initially have plans of launching the attack. The commanding general of the first division wishes to coordinate simultaneous attack, distributed system. Neither general will decide attack unless he is sure that the other will attack with him. So they have to communicate, and they communicate by a messenger. It takes messenger 1 hour, let's say 1 hour, to get from one to the other. However, it is possible that messenger would get lost in the dark or be captured by enemy. Fortunately, on that particular night, everything goes smoothly. Question: how long will it take to coordinate the attack? You can retranslate it into the messaging in a distributed system. So, suppose the messenger sent by General A makes it to General B with the message attack it down. Will General B attack? No. since A does not know General B got the message. So, might not attack. General B sends messenger back with acknowledgement. Suppose the messenger makes it. Will General A attack? No, because A is worried that General B does not know A got the message. That General B thinks A might think that B did not get original message, and thus General A does not attack. And General A sends messenger back with acknowledgement. And this is not enough. So no amount of acknowledgement sent back and forth will ever guarantee an agreement, even in the case that messenger succeeds in delivering the message every time. All what is required is, in formal reasoning, is the possibility that messenger does not succeed. To solve that problem, created Halper and Moses in 1985, created a propositional modal logic with M agents. They prove in a beautiful formal way this logic to be essentially a multi-agent version of the standard modal logic S5. They also prove formally that the common knowledge is not attainable in system where communication is not guaranteed. Of course, the generals was just to make a story, but it was all about the distributive system and the communication in distributive system. So, and they proved that the common knowledge is also not attainable in system where communication is not guaranteed, as long as there is some uncertainty in message delivery time. In a distributed system where communication is not guaranteed, common knowledge is not attainable. Nicely. But we often do reach agreement. So they prove also formally, that's why you have course of logic, that they prove that formally defined common knowledge is attainable in such models of reality where we assume, for example, events can be guaranteed to happen simultaneously. Moreover, there are some variants of the definition of common knowledge, because what is a common knowledge, that is attainable under more reasonable assumption. So finally, we can formally prove that when and that we often do reach agreement. So that was computer scientists. Now, it's very important, the whole field of reasoning in AI. So reasoning in AI, when you think about AI, you have basically two assumptions. That we need flexibility of reasoning, which is one of key property of intelligence. And assumption two, that common sense inference is defeasible in its nature. That we are capable of drawing conclusions, acting on them, and then retracting them if necessary in a face of new evidence. And if computer programs are to act intelligently, they will need to be similarly flexible. So the goal is develop formal systems, logics, that describe common sense flexibility. And flexible reasoning, this is like Russell paradox for set theory. Rater, 1987. Consider a statement, birds fly. Tweety is a bird. From this and the fact that birds can fly, we conclude Tweety can fly. Well, Socrates all humans are mortal, I am mortal, I am human, I am mortal, right? So we have words. This conclusion is defeasible. Tweety might be ostrich, a penguin, a bird with broken wing, or bird whose feet has been set in concrete. They have hundreds of very funny examples. So this reasoning is non-monotonic reasoning. We'll talk about non-monotonic logics. On learning a new fact, for example, that Tweety has a broken wing, we are forced to retract our conclusion that Tweety could fly. So these are called non-monotonic reasoning. And we have, if we want to have robots, if you want to have a real AI, you have to have a formal way of proving that such reasoning is correct. So we have definition, and a non-monotonic reasoning is reasoning in which the introduction of new information can invalidate old facts. Now you have another, that's called non-monotonic reasoning. Default reasoning, or default logic, is a reasoning that let us draw plausible inferences from less than conclusive evidence in the absence of information on the contrary. Of course, non-monotonic is, this is more general, it's an example of default reasoning. And again, we have to develop theory and prove things about the default reasonings and what we can use and which are the laws of default reasonings. And now, this is another reasoning, belief reasoning. And this is example Moore, 1983. Consider my reason for believing that I do not have older brother. It is surely not that one of my parents once casually remarked, oh, you know, you don't have an older brother. Or have I pierced it together by carefully sifting the evidence. I simply believe that if I did have an older brother, I would know about it. Therefore, since I don't know of any older brother of mine, I must not have any. So that is a belief reasoning. So that was, I read it very carefully because that is like Russell paradox, nicely original statement. The brother example is not default reasoning and it's not non-monotonic reasoning. That is reasoning about one knowledge or belief. So we have a new type of reasoning. I've put a definition. Any reasoning about one's own knowledge or belief is called autoepistemic reasoning. So we have autoepistemic reasoning, we have autoepistemic logics, we have the whole research into a formal theory of autoepistemic reasoning. So autoepistemic reasoning models the reasoning of an ideally rational agent reflecting upon his beliefs or knowledge. And the logic which describe are called autoepistemic logic. We have one more, which is one of my, it really moved a lot. So McCarthy, which is like a father of AI, and took the cannibal problem. Right? The cannibal problem, everybody knows. 3 missioners and 3 cannibals come to the river. A robot that sits 2 is available. If the cannibals ever outnumber the missioners on either bank of the river, the missioners would be eaten. How shall they cross the river? And of course, you know the solution. Boo, 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 boo. Right? So that is our our solution, how you do it, right? Initial state is 331, the desired state is 0, 0, solution is given by the sequence. Beautiful problem solved. But imagine now giving someone this problem, and after he puzzles for a while, suggests, go upstream half a mile and cross the bridge. What the bridge, you say? No bridge is mentioned in the statement. And he replies, well, they don't say there isn't a bridge. So you modify the problem, exclude the bridges. And he poses again a helicopter. Or you exclude that. He proposed winged horse. And then you tell him your sequence of solution. He attacks the solution on the grounds that the boat might have a leak. After you rectify that omission of the statement, he suggests a sea monster that swim up the river and might swallow the boat. Finally, you must look at the mode of reasoning and which would settle that problem. So that was McCarthy. And he proposed something which he calls circumscription as a technique of solving. He argues that that is a part of common knowledge that the boat can be used to cross the river unless something is wrong or something else prevents using it. And then and our facts do not require that there be something that prevents crossing the river. That's circumscription, which is what will generate a conjecture that there isn't, and they put the very beautiful formal solution to that. And also it happened that that technique is connecting with negation in logic programming and so on. So that moved a lot of people and a lot of thinking. But this is in real life, how to handle problems like that. And then it's just I just wanted to give you some definition. So first, logical paradoxes, they're called logical antinomies, are the paradoxes containing notion of set. Semantic paradoxes, we talk about semantic paradoxes, are paradoxes that deal with the notion of truth. And non-monotonic inference is the reasoning in which introduction of new information can invalidate old facts. And we have a fact. Non-monotonic reasoning is an example of default reasoning, and we also talk auto-epistemic reasoning is the reasoning about one's own knowledge or belief, and auto-epistemic reasoning models the reasoning of an idly rational agent reflecting about this beliefs or knowledge. So that is the part, like short putting together the part of computer science puzzles, and now would be we'll solve all those problems. They've been solved. Okay, thank you very much.